This is the Level 2 2019 Waves paper, question 2. Right, we got fibre optic networks being installed throughout New Zealand to increase communication effectiveness and efficiency. Optical fibre consists of core cladding as shown below. Initial stage requires a beam infrared waves to be sent into the fibre optic cable so it can be transmitted along great distances. Diagram below shows infrared waves travelling from air into the core. So we've got air, core. This is the normal line, or the line perpendicular to the boundary. It's a terrible square. It's meant to be like a perpendicular square. When you normally do this, it's this angle here is the angle that you normally use when you're using Snell's law. If you're comparing apples with apples, you always compare from the normal to the ray, normal to the ray. So this is 36 degrees. 90 minus 36 minus 36 is 54 degrees. So 54 degrees. So the angle from the normal to the ray is 54 degrees. It's just convention. They throw this in here just to mess you up. It's just to stop kids that have no idea what they're doing. Right, calculate the angle theta 2, this one here, if angle 1 is 36 degrees. This like theta 1 is 36 degrees. If you use this as your angle, you'd end up finding this angle here, I think. Yeah, probably. Yeah, because it'd be like the co-angle of it, I assume. Anyway, this is Snell's law. So N1 sine theta 1, that shouldn't be a dash, is equal to N2 sine theta 2. What am I trying to find? I'm trying to find theta 2. So N1, I'm going to divide both sides by N2. N1 divided by N2 sine theta 1 is equal to sine theta 2. In other words, theta 2 is equal to, you take sine inverse of all of this. You take the sine inverse of both sides, it just gets rid of the sine. Sine inverse n1 over n2 sine theta 1. There we go. And this is equal to sine inverse, what's that index? So this is the first, this is n equals 1, n1, and that's just 1 because it's air. The index of refraction of air is 1. Glass, it says it right here, is 1.45, n2 1.45. I always just write it on the actual thing because then you know what you're looking at. So it's going to be 1 over 1.45 sine, what's it, 54 degrees, 54 degrees, and that is going to be equal to is 33.91 degrees. You see, I just did the first lot of stuff out of the brackets, and I went sine answer. If you go shift answer, it just brings shift answer brings up the previous answer that you had. So that equals 33.91 degrees. So theta 2 is equal to how many SF? Just round up to 34 degrees because that's 2 SF. Name and explain the physics phenomenon that occurs at the air core boundary. It's refraction. If you go from one medium to another, it's refraction, and it's because it changed the light. The light waves change velocity or change speed. I'll just pause it and write it a little neater. Right, so I said refraction occurs when light changes velocity when it passes from one medium to another, and then I've just put as it changes velocity, it changes speed and direction. Technically, I suppose you can say that the light travels slower in glass than it does in air, although it's a lot more complicated than that in reality. In reality, the light does travel the speed of light inside the glass. It's just the glass has, was it silicon dioxide? So the silicon atoms and the oxygen atoms have electrons on their outer orbitals. Electrons create electromagnetic waves. When light as an electromagnetic wave comes in and interferes with the electrons that are on the outer orbitals, you get a total wave that adds together. So the light wave plus the electrons wiggling around their little electromagnetic wave, that makes one net or one total electromagnetic wave, which is slower than light would have been by itself. It's not that the speed of light actually changes. It's more nuanced than that. But anyway, enough of that. It's only year 12. You don't need to know about that. Right. As the beam moves through the optical fibre, continually rebounding off the walls, for this to occur, the cladding must have a lower refractive index than the core. That's true. Name the phenomenon that allows this process and give a comprehensive explanation why it's important that cladding has a lower refractive index than the core. It's called total internal reflection. And when you go from a slower medium, so a medium with a higher optical density or higher refractive index, to a lower refractive index, light bends away from the normal. And if you get to a point where light bends so far away from the normal, it just totally internally reflects. So I'll just pause right up the answer and then explain what I've written. Right, so I said it's total internal reflection. When light passes from a high refractive index to a low refractive index, the rays bend away from the normal. If the incoming ray is large enough, I should have said large enough, brackets, greater than the critical angle, the outgoing ray will be larger than 90 degrees. Technically, it won't be larger than 90 degrees. It just won't exist. But there's a way to think about it. So it'll reflect instead. I think that's really about as much as you could say. Maybe you can like chuck in, if when you do this, maybe I could have written more. I could have said like for refractive index, brackets, optical density, so high optical density. It's just it's like a synonym for refractive index, but I mean, yeah, I'm not really sure what they're really looking for for this question, but I think that's basically what they're looking for. Well, I already know what they're looking for, but even looking at the mark schedules, it's kind of a weird question. Anyway, infrared waves have a frequency of 3.53 times 10 to the 14 hertz. Speed of light is that. Refractive index is that. First, by determining the wavelength of the incident ray in air, calculate the wavelength once it's entered the core. So that's the frequency in air. That's the speed of light. Where's the speed of light? There's the speed of light. That's the frequency. So in your formula, you've got a equation. Velocity equals frequency times wavelength. In other words, wavelength is equal to divided by both sides by frequency. So velocity divided by frequency is equal to 3 times 10 to the 8 divided by 3.53 times 10 to the 14, and that is equal to 8.49 times 10 to the negative 7. So 8.49 times 10 to the negative 7 meters. It's 849 nanometers, so that is actually infrared light. I like how they actually are consistent with this. What do we got? Has that moved? But first, calculate the wavelength of the ray once it's entered the core. So in your formula sheet, you have, where is it? There it is right there. Index of refraction divided by index of refraction is equal to velocity over 1, velocity over 2. These numbers all come from the ratio of velocities. It's all derived from the ratio of velocities, and it's all to do with frequency conservation. Because if you move this V up onto that side, velocity 1 onto that side, if you have velocity V1 over lambda 1 is equal to V2 over lambda 2, because V2 over lambda 2, you go V2 over lambda 2, that is just equal to frequency. And it's conservation of frequency, which is essentially conservation of energy. This is why this equation exists. The index of refraction are just unitless measures. They tell you what percentage of the velocity. So if it's, index of refraction of 1.45, that means we get the speed of light and divide it by 1.45, and that'll tell us the new speed in the glass. Right. We'll write that out, shall we? So N1 over N2 is equal to lambda 1 over lambda 2. N1 is air, lambda 1 is that one there. That's the wavelength in air. We're trying to find lambda 2, so we'll flip both sides. So we get lambda 2 over lambda 1 is equal to N2 over lambda 1. And then we'll times both sides by lambda 1. So in other words, lambda 2 is equal to N2 over N1 times lambda 1. There we go. Right, I'll just calculate that now. Oh, do I chuck the numbers in? Yeah, I'll chuck the numbers in. What's N2? 1.45? 1.45 divided by 1 times 8.49 times 10 to the negative 7. Just realised I made a mistake. This is lambda 2, that is lambda 1. So that'll be lambda 2, that'll be lambda 1. This will be n. Hold on. Yeah, I think that's right. It ends up being. I'll just scribble this out. I'm completely dyslexic with this sort of stuff. This is what happens on a rush. This should be lambda 2 is equal to. Move the n1 up. Hold on, wait. Flip both sides so we get. Ooh, just let me think about this. This is lambda 2. I did have that muddled up, didn't I? Yeah, that's lambda 1. So we're going to try and find lambda 2. So it's n1 over n2 times lambda 1. And that is equal to essentially 8.49 times 10 to the negative 7. Oh, there we go. Divided by 1.45. And that equals 585 times 10 to the negative 7. So 5.85 times 10 to the negative 7 meters. The reason why I say 585 times 10 to the negative, the reason why I say 580, this is I'm always used to dealing with nanometers. This is very confusing going back to doing level 2. It's 585 nanometers, which is essentially green light. Green light's about a little past green light, so maybe greenish into orange. Probably not quite. Probably quite green, little-ish orange, depends on how good your eyesight is. And this makes sense to me because I know that when you go from, what do you call it, like a faster medium to a slower medium. If you think about waves in water, faster medium to slower medium, the waves get bunched closer together, which means the wavelength will get less, and we've gone from 8.49 to a 5.85, which makes sense. You can think about it, water waves, I think there's some examples when you learn for waves, they do get close together when you go from a fast medium to a slow medium because the previous waves catch up to the ones in front.